So, as I have gone through in the previous slides, we can basically view transistors as switches. So, MOS transistors are electrically controlled switches. The voltage at the gate is what controls the path from the source to the drain. So, here's basically showing what I mentioned in the last couple slides, a little bit more consolidated and summarized. So we have an NMOS transistor, has a gate, source, drain. Typically we don't show the bulk, we just assume that the body of the NMOS is connected to the source or connected to the lowest voltage, which is ground. And so if we connect the gate to ground and we call the gate value as 0, then the transistor is turned off and it's a switch that's off and doesn't allow any current to flow from drain to source. If we connect the gate to the highest voltage, VDD, we call that a logical 1, and that will turn the NMOS transistor on, and the on switch will connect the drain to source and allow current to flow from the drain to the source. For a PMOS device, as I mentioned in the previous slide, we draw that as a transistor with the bubble at the gate because it's inverted compared to the NMOS device. And for the PMOS device, the bulk isn't shown again, but the bulk will be connected to the most positive voltage in the circuit, so it'll be connected to VDE. And if the gate for a PMOS is connected to ground or 0, then the switch is turned on and it will allow current to flow from the drain to the source. So this is inverted behavior from the NMOS, as you can see above. And for the gate of the PMOS, if the gate is connected to a logical 1 or VDD, then the transistor will be a switch that's off and will not allow any current to flow from the drain to the source. So here we have one of the simplest circuits that we can construct with CMOS devices, which is a single NMOS device connected in series with a single PMOS device between VDD and ground. So if we have the source of the NMOS device connected to ground and the drain of the NMOS device connected to the drain of the PMOS, and then the source of the PMOS connected to VDD, and where the drain connections are connected together, that will be our output, which we're calling Y, and the gates are connected together as well, and they're connected to our input, which we will call A. So on the right hand side, that shows the circuit level diagram or transistor level diagram of this circuit. If you look in the lower left corner, you'll see the symbol level diagram of this circuit, where that triangle with the circle on the right hand side is representative of the transistor level diagram on the right side, but it's an easier way of depicting it. And so a lot of times you'll see these symbols that stand for a certain amount of logic that will be used to make the circuits a little bit more understandable. And we'll get into more of these symbols later. But this symbol with the bubble or circle on the output there is showing that this is inverted logic. So those bubbles tend to represent inversions going on. So with an inverter circuit like this, that means that Y, the output, is an inverted value of A, the input. In this particular case, there's only one input, one output. So we'll go through the behavior here quickly. If we have an input of 1 to A, that's a logical 1, which represents it's at the value of VDD. This will cause our PMOS transistor, if you remember from the previous slides, if the gate of a PMOS transistor is 1, then the transistor will be off. But it will cause the NMOS transistor to be on. This means that our output Y is directly connected through that NMOS switch to ground, and it has no connection to VDD. So our output value of Y will be 0, ground, or a logical 0. And so an input of 1 causes an output of 0. Now if on the other hand our input A is connected to 0, this will cause the PMOS device, from our previous couple slides, the PMOS will be turned on as a switch and the NMOS device will be turned off. This now means that our output Y has a direct connection to VDD and no connection to ground. So Y will be pulled up to VDD, which is a logical 1 value in the circuit. So our output is 1. So this CMOS inverter causes us to have whatever input is coming in be inverted to get an output value. So a 0 at the input creates a 1, logical 1 at the output. Logical 1 at the input creates a logical 0 at the output. So now that we've covered a very simple logical function, let's go on to a slightly more complicated logical function. That would be the CMOS NAND gate, or NAND function. In this case, you can see that there are 4 transistors involved, 2 NMOS transistors and 2 PMOS transistors. Typically in CMOS, the C stands for complementary. And it's complementary from the standpoint of the number of transistors in the NMOS going to ground are typically always equal to the number of transistors of PMOS going to VCC, but just organized differently, so that we get the logical function out. So that's why the C in CMOS stands for complementary, and you'll see patterns as you go forward in how this logic is organized. But in this case, we'll see that we have 2 NMOS in series with each other. The source of one NMOS connected to ground, the drain of that NMOS connected to the source of the next NMOS in series, up to the output signal Y, and the 2 PMOS transistors are connected in parallel with both of their drains connected together to the output Y and both of their sources connected together, and that is connected to VCC. It's a little bit, the notation there is not as obvious, but that rail that's connecting them is supposed to mean a VCC rail. Again, the PMOS devices have the bubble, so you can tell the PMOS versus the NMOS. Now in this case, one of the NMOS is connected, the gate of one of the NMOS is connected to one of the PMOS, and that's connected to an input signal A. The gate of the other NMOS is connected to the other PMOS, and that's connected to input signal B. Again, the right-hand side shows the transistor level diagram. The lower left-hand side shows the 2 different types of symbol diagrams that you can use for this logical function. The uppermost of the 2 symbols is an AND gate, the basically flat line on the left side and the curve on the right is how an AND gate is, but with the bubble on the output, it's an inverted AND gate, which is called a NAND function, not AND. So the NAND gate there is the upper one. The lower one is an OR gate, but with bubbles on the input. So it's doing an inverse of each of the A and B inputs, and then doing an OR of that function. And this is just showing, if you go back to logical functionality that you should have learned in other classes, there's something called De Morgan's rule, where you can take the output of a given type of gate and invert the output and invert both of the inputs and then convert an AND to an OR. So you can see in this case the output went from a bubble on the output to no bubble on the output. The inputs went from no bubbles on the input to bubbles on the input, and the AND went from AND to OR. So that's using De Morgan's rule to change how you think about the logic. Transistor-wise, it's exactly the same transistor function, and you will get the exact same function out of both of those symbols. That's how De Morgan's rule says that the NAND is the exact same functionality as a NOT OR. So let's go through the logic quickly. So in this particular case, if we have A and B are both 0, that means both of the PMOS devices are turned on. Both of the NMOS devices are switches that are off. That means you have two different connections up to VCC. You have no connection down to ground, and you will get a 1 value out for 0 and 0 in. In the next case, if we have A is a 0 and B is a 1, the A being a 0 causes its PMOS device to be turned on, but its NMOS device to be turned off. So from Y, if you try going down the NMOS stack, you immediately hit an OFF gate, but you have at least one ON gate going, switch turned on going up to VCC. So you have no path down to ground because the first gate you hit, NMOS gate, is off, and you have a path up to VDD. So you get, for a 0 and a 1 input, you get a 1 output because you have a connection up to VDD. For the next case where A is 1 and B is 0, in this case the B input PMOS, connection to PMOS, that PMOS will be turned on, so you'll have a direct connection up to VDD through that PMOS. Since the A input is a 1, the first NMOS device will be turned on, so you'll have a connection from Y through the first NMOS device to the second one, but the second one is turned off, so you have no connection down to ground. So you'll have a little bit of a connection or partial connection that basically gets cut off partway through. So you have a connection up to VDD, you have no connection to ground, and you get a 1 output, a logical 1. Now when both inputs are connected to 1, then both PMOS devices are turned off and you have no connection up to VDD. But both NMOS devices are turned on, so you have a connection through the A NMOS device and the B NMOS device down to ground, and it will cause your output Y to be connected to ground, and you get a logical 0 out of the circuit. So this set of transistors connected like this gives you a functionality of a NAND, which is if your input, only if both inputs are 1, you get a 0 out. So that's a not AND. Normally with an AND gate, you only get a 1 out if both inputs are 1, and you get a 0 if you have either input 0. A NAND gate is not AND, so it's taking an AND and inverting it. So in this case, if any input is 0, you get a 1 out, and if both inputs are 1, you get a 0 out. So this circuit shows the other most basic logical functions for CMOS, which is a NOR gate. In this case, it's similar to the NAND gate. We have 4 transistors composing this logic, 2 PMOS and 2 NMOS transistors. The NOR functionality is kind of complementary or flipped compared to NAND, where you can see in this case the 2 PMOS transistors are in series with each other instead of in parallel.
So you have the first PMOS transistor, its source is connected to VDD, the top one, and then its drain is connected to the lower level PMOS transistor, the source of that transistor, and then that PMOS transistor, its drain is connected to the output signal Y. That is also connected to the drains of both NMOS transistors, which are connected in parallel to the output through the drain, and there's the source of each of those NMOS transistors is connected in parallel with each other to ground. Now there's two inputs, input A and B. Input A is connected to the gates of one PMOS transistor and one NMOS transistor, and input B is connected to the other PMOS transistor and the second NMOS transistor. So the right hand side shows the transistor level diagram again. If we look at the lower left hand side, we see the symbol diagrams for this functionality. And again, there's two symbols because the De Morgan's theorem says that there's two kind of ways of writing the logical function, but will have the same functional behavior. So one is a NOR inverted, so or an OR inverted, so an OR not function with the NOR symbol with the curved left hand side, and then the bubble at the output is for an OR gate inverted, an OR not, or a NOR gate, and then the bottom symbol is with the flat left hand side is an AND gate symbol, but with the bubbles at the input, meaning that the inputs are inverted. So it's like a not A and not B type function, which is the same as an A or B not function. So that just shows the different symbols that produce the same function as a NOR. So going through the logical function, this truth table has already been totally filled in. So if we have A and B are both 0, then that's going to cause the two PMOS devices to both be on, the two NMOS devices to both be turned off. So we will have a path through the PMOS devices to VDD, and we will get a logical 1 on the output. Now, in all of the other three cases where either of the inputs, so if input A is a 1, or if input B is a 1, in either case, we are going to have one of the PMOS transistors turned off. So we will have no path up to VCC, and in either of those cases where one of A or B is on, one or both of the NMOS devices will be turned on, and so we will have a path to ground or 0. So you can see for the following three cases where A or B, either one of them is a 1 or both of them is a 1, we will get a 0 out because we will have a path to ground and no path to VDD. So that gives us our logical function for a NOR gate. So for now, I'm just going to go through one more example of a logical gate, which would be a 3-input NAND gate. So this, I'm going to go through a little bit of a thought process at the beginning. So let's say for a 3-input NAND gate, how would we construct that? Basically, what we want for a NAND gate is if all inputs are 1, we want the output to be 0. If any input is 0, we want the output to be 1. So if we have a 3-input NAND gate, think about it for a second. How would you do that? Again, you can go back and look at what the 2-input NAND gate looked like, and how would you modify that
in order to create a 3-input NAND gate. So I'll give you a little bit of time to think, maybe try and sketch it out, and then we'll continue on in a second. So if you need more time, you can go ahead and pause, but I'll go ahead and show you the answer right now. So this is very similar, if you think about it, to the 2-input NAND gate. Instead of having 2 NMOS in series with each other and 2 PMOS in parallel with each other, we now have 3 NMOS in series with each other, 3 PMOS in parallel with each other. And you can see here that if only if all inputs are 1 are you going to have all 3 NMOS on and all 3 PMOS off, and which will cause you to have the output pulled to VSS and no connection to VDD. And if any input is 0, you're not going to have a path down to ground, and you will have a solid path up to VDD through one of the 3 PMOS devices. So this does the logical function of a 3-input NAND gate that you would want.